So now in this video, we're going to use the hex inverter. There's 6 inverters to make a buffer. So the buffer means what the input is, the output will be. But this is not a buffer integrated circuit. It's NOT gates. But you can combine the NOT gates. You just put a couple of them in series. So there's also a NAND gate. It's like an AND gate, but the opposite. You can combine those to make literally any other logic gate. All kinds of circuitry, just with NAND gates. But the NOT gate, we can, invert the signal and invert it again. Ultimately, getting the output to be what the signal is. So that's what we're doing here. We're combining a couple of them. So the first NOT gate is 2 right there. And then the second one over here would be number 1 when you look at the circuit here. But the main takeaway is we're using NOT gates, but we have a high input, a high output. You can see that side of the LED, the short lead, the cathode, is to ground. So the output there is connected to the positive supply as good as it can be. I lower the voltage, and remember, this is a Schmitt trigger NOT gate, so there's a middle ground hysteresis right there. You can see the output is either high or low right in this range there. But here's the upper threshold, and down there is the lower threshold. So lower threshold, you go below that and you got a low output, blue LED. So positive supply to the long lead, the anode, short lead, the cathode, heads to the output. So the output is connected to ground if the blue LED is lit up. And yeah, it's that simple. Of course, this is a integrated circuit 7400 series. First off, they're like susceptible to shock, so I try to discharge myself before I touch any of the circuit if I built up any static charge or anything. And also, the inputs are very sensitive to stray signals and stuff. And so if you just leave them floating, they could cause oscillation. So I just got them to a supply voltage. You could use resistors instead. So that's anywhere you see an A right there. There's a jumper. Of course, you have to power the integrated circuit. They don't always show that on schematics. Usually with logic gates, they don't show it. But even op amps, sometimes they'll show the supply voltage or they won't. You always have to power the integrated circuit. So we're using 2 of them. Number 2 and number 1. We get a high input. I'll go back and do that. And the inverter that we got here. So that's our input, obviously. You should be able to follow that. The output for that input is down 1. So that's our output. So it's going over that input, over that output to the input of our number 1 right there. And so if I set high there, we got low up here, and then it inverts it for high coming out, positive. And we got the red LED. So that's not as easy to follow as the schematic, I don't think. So high input is low output for that inverter, but that's the input for the next inverter for a high out. So high, low, high, and we got a high output, positive supply, red LED lights up. If we turn this low, just get down whenever it's low enough, then we have a low input, which becomes, or a low output, I mean. Yeah, low input, high output, that's what I should say, which is a high input, which is the low output. You can see the blue LED headed to ground. It's easier if you write it out like this. Low input, high output, and then it's flipped again to a low output, which means it's connected to ground. The blue LED will light up as good as it can. Doesn't make a perfect connection to ground. I always realize that. The outputs have limitations. The integrated circuit has limitations. Looks like we can work with 2 to 6 volts right there. Each output can handle about 25 milliamps of current. So if you're lighting LEDs with these, it works pretty well right there. But there's a maximum of 50 milliamps. So there's 6 of them right there. Obviously, if all 6 of them were doing 25 milliamps of current, I think that is 150 milliamps total. You can't do that. You got to taper them down so that there's only 50 milliamps total. So like less than, or about 10 milliamps of current each of them. Yeah, slightly less if you had all 6 of them wired up to a circuitry. Be aware of that. So in case. That is what we got there. We took the inverter, just combined a couple of them and made a buffer. So that's why you're going to see inverter symbols if you look at schematics, and they're probably going to be Schmidt trigger too. But that's why you're going to see them a lot more than buffers. Buffers would just be a triangle. And the reason why is because if you have an inverter integrated circuit right here, especially if you need at least one in a circuit, then you have 5 more over here. You can just take a couple of them and combine them, and now you have a buffer. You don't need a completely different integrated circuit. And of course I added the truth table. So high in is high out, low in is low out, because we made a buffer, even though we're using inverters right there. You combine these, now you got a buffer. And again, there's the NAND gate, a NOT AND gate. You can combine all, those to make all kinds of circuitry, but definitely all the other logic gates. So yeah, that's about it. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.